Hey guys, this is Madhav. I'm going to talk to you about circuits that can count up because, well, counting is very useful, not maths that's useful when you're working on practical engineering applications. If you're not sure what the words that just came out of my mouth were, or you're not sure about the words in this yonder bubble, not the best video for you. However, if you know the things that are on the screen, except for this thing, the goal of this video, what we're going to build up and explain, then you're in the right place. Let's talk about synchronous up counters, meaning synchronous meaning we want to do things that are very predictable. We want things to change at the same time. We want numbers that change, counts that go up at about exactly the same time. We're going to start by analyzing some patterns in the way that we count. So I have noted this table over here that shows some numbers that are just being increased by one on each clock cycle on our flip-flops. So by clock cycle, I mean on each rising edge of the clock signal that the flip-flops will be receiving. As you can see, here it's clearly easy to say that we increment by 1 until we get to 7. At that point, we can't, go any higher because we only have 3 binary digits in this case, so we go back to 0 and start again. Now, it's looking at this binary representation of our, count upwards that we'll see the pattern we need in order to build our asynchronous, no, our synchronous up counter. In particular, I have highlighted the pattern for you. It's related to how many ones there are to the right of any particular bit. So let's start with this first red bit over here. It has no ones to its right because it's the rightmost bit. So you can think of what's going on as, okay, there are, there are the maximum number of ones to the right of this bit, because the maximum is just 0. There cannot be any more ones to the right of the bit. When this thing happens, when this condition happens that you have the maximum number of ones to the right of some bit, that bit, it will toggle. In fact, we see the same thing here because, all of these cases, they have the maximum number of ones to the right of some bit, right? So again, 0 ones to the right, that's because that is the maximum. There cannot be any more ones to the right. The bit will toggle, the bit will toggle, the bit will toggle, and so on. It's the same thing over here. I suppose I can draw that in as well. So if you look at these two cases where this middle bit is being highlighted in red, the reason is that you have one bit to the right that is a 1. And in this case, well, that is the maximum number of ones that can be to the right of this bit. So when you have the maximum number of ones to the right of this bit, you can see that it toggles. Here, you see that the bit doesn't change. Why is that? Well, you don't have the maximum number of ones to the right of the bit. You only have a 0, you don't have 1. But here, now you can see you do have the maximum number of ones. You only can have one 1 here, and so the bit toggles again. And the pattern keeps on repeating. No toggle, because you haven't reached the maximum number of ones. You have a toggle, because you've reached the maximum number of ones. No toggle, toggle, no toggle, toggle, and so on. Finally, if we look at this third most bit, you can see it stays the same here because you have 0 ones to the right. That's not the maximum that you can have to the right. stays constant here because you have one 1 to the right. That's not the maximum number of ones you can have to the right. Again, only a single 1 to the right stays constant. Now you see we have two ones to the right of this bit. That is the maximum number of ones that can be to the right because there are only two bits to the right. And so the bit toggles. This pattern repeats. The next time the bit toggles is over here because you've reached the maximum number of ones, two ones that can be to the right. Um, I drew in like a, in bracket 0 because you can think the pattern extends. So because you have reached three ones to the right of this 0, and that's the maximum number of ones that can be to the right, this count should be like 1000. Because we only have three binary bits, that can't happen, however, which is why we go back to 000 and start the process again. So the key inside, just to put it into words, um, some bits, I won't use mathematical notation in case it's confusing. Some bits, some bit out there, it will toggle when all the bits to the right of it are 1. Hopefully that pattern is clear to you. Keep staring at the table. If not, anyways, this is the key insight that we need in order to design our synchronous sequential circuits. So what are we gonna do? Well, okay, so this rightmost bit, it will toggle all the time because, it's always the case that it has the maximum number of ones to the right of it. It has always 0 ones to the right of it. There are no bits to the right of it. That's the maximum number of ones you can have. So I'm going to start off by drawing a toggle flip-flop. It's going to represent a rightmost bit, which I will call Q0, because it's the least significant bit, and this is, a least kind of number. How do we want to toggle it? Like I said, it's always toggling, because, always you have the number of ones, the maximum number of ones to the right. So I'll just put in a 1 here. Now we can just feed in a clock signal and we can see, okay, every single cycle the bit is toggling, so the bit must be toggling on just the regular clock input. Whenever you have a new rising edge, whenever you have a new cycle in the clock signal, the bit will toggle. Okay, one bit down, two to go. How do we do the next two? The next two, well, you might agree that they are a little bit more tricky. In particular, the tricky part is that we need the bit to the right to be a 1 before we toggle these bits to the left, right? That's the pattern we just analyzed. Okay, so this Q0 represents the bit to the right. When this is a 1, then we want the next toggle flip-flop to toggle. I'm going to draw in that toggle flip-flop here. So this is going to be Q1 because 1 is larger than 0. This bit is larger than the last bit. How do we do this? So we want this thing to be a 1 and then we want to toggle. Okay, well, why not just wait for it to be a 1? When it's a 1, the toggle will be a 1. When it's a 0, the toggle will not be a 1. That fixes our issues, We just wait for this thing over here to be a 1. When it's a 1, then we toggle. Which clock signal do we use? Remember, we want a synchronous sequential circuit. We want the outputs to all update on the same rising edges. So because we want, the same almost instantaneous updates, we're going to use the same clock signal across all of our toggle flip-flops. As you might guess, with me saying all of our toggle flip-flops, we're going to have another one because, we need another one to represent another bit. This is our last bit, Q2. Whoops, Q2. We can predict what the clock signal will be. I just explained it. We gotta have the same clock signals everywhere. We want all of these flip-flops to change nearly instantaneously on the same rising edges. However, now we have an issue. We cannot just take Q1 and connect it to T, because if we did that, then the circuit would update when Q1 is equal to 1. But that's not what we want. We want the circuit to update, particularly this leftmost column. We want this column to update only when all numbers before it, all bits before it are a 1. Not just this thing is a 1. You can see no update here. It has to be these two are both a 1. Then we will update. So what do we do here? We want to make sure this thing is a 1. We want to make sure, this Q1 is a 1. We want to make sure this Q0 is a 1. Well, if we want two things to be a 1, and then we want to toggle, so we want to set this to 1, we want Q0 is equal to 1, Q1 is equal to 1 to produce a toggle equal to 1, because that's when we want this Q2 to toggle. How can we take two inputs when they're both 1 produce, an output of 1? We just use the AND gate, right? We just got to take Q1 and Q0, feed them into an AND gate, and when these are both 1, then our toggle will be equal to 1. So that's what we're going to do. So we have Q1 over here, we have Q0 over here. I'm just going to take it over. We're a little bit cramped for space here, so you'll have to forgive my tiny drawing, but we just have this thing drawn a little bit more messily here. This is our asynchronous sequential circuit, our synchronous sequential circuit. It waits for all the bits to the left to be a 1 before the next bit will toggle. And as you can imagine, we could continue the pattern forward. So if we wanted to extend this into the next toggle flip-flop, let's say we had a 4th bit. Again, just pipe in the same clock, and we have to be careful, right? We want all the bits to the left to be a 1. So if we, tapped into this wire over here, we're just checking that Q1 is equal to 1. If we tap into this bit over here, that's when we're checking, okay, Q0 is 1, Q1 is 1. That's when this will be a 1. So now we can pipe this in here and feed it through there. And you'll keep seeing this, tap off the main wire, feed it into an AND gate, tap off the main wire, feed it into an AND gate, keep that pattern repeating. In fact, we could, tap over here if we wanted to, and then make this an AND gate. You might think, okay, what's the point of that? That's just 1 and whatever. The 1 isn't gonna change anything. That's right. However, sometimes we don't just, we set this to be a 1. We might have an enable signal, which might say, okay, only when the enabled signal is on do we want the flip-flops to be, counting up. Otherwise, we don't want any counting up action. And you can see if the enable signal is set to 0, then this toggle is 0. 0 and whatever is 0, so this toggle is 0. 0 and whatever is 0, so this toggle is 0. You can keep the pattern going. All the toggles become 0. So as you can see, we are done. This is our synchronous sequential circuit. It solves the problems of asynchronous sequential circuits, asynchronous circuits to count up, namely that all these different flip-flops, they don't have as large of a delay, as noticeable of a delay between one flip-flop changing to another, because all of them, they're changing on the same rising edge. There we go. That's it.